This is chapter 4 on apportionment methods. When a vaccine for COVID-19 was found, Pfizer initially had 25 million vaccines available. How many of the vaccines should each state have received? That is, what should be each state's apportionment of the vaccine? So imagine that everybody wants a vaccine. Maybe we don't have enough for everybody, but each state says, I want some, I want some. So we give each state a portion of the total vaccines we have, and we want to give it proportional to how many people they have in each state, right? So this chapter deals with a special kind of discrete fair division. So you don't have to worry just about the word discrete right here, but just a fair division problems, a special type. In chapter 3, each player was entitled to an equal share of different objects. In chapter 4, the objects are all the same, but players get different sized shares. The number of teachers assigned to each school is, so here's some examples problems we might see. The number of teachers assigned to each school in a district based on student enrollment. So maybe they hired 200 teachers. Like, how are we going to give them out to the schools? Well, we're going to do it proportional to the number of students that are at each school. You know, if a school is overloaded with students, they're going to need more teachers, right? And then a school that doesn't have as many students that year is going to need less teachers, you know? The number of nurses distributed to different units in a hospital based on the average number of patients. And also another problem we'll see is city buses apportioned to different routes based on the average number of passengers. And the number of seats each state. And this is really, I feel like this is where the problem really originated and where this type of mathematics really originated, was when Congress was trying to give out seats in the Senate. You know, you guys hopefully know, there's 100 seats in the Senate, and there's so many seats. I think there's 235. Can't remember. That's at least that's what when I studied it, there was 235 seats in the House of Representatives, and we give seats in Congress. Wait. Well, of course each state gets 2 senators, but the House of Representatives, you're given seats in the House of Representatives based on how many people you have in your state. So that's really where this problem really came from, is they were trying to give seats in Congress and proportional to the amount of people in each state. And they had to have it be the exact number. Okay, sorry about that. So we have the the page up here again. All right. We will discuss 5 apportionment methods. Hamilton. So if you know your history, you know that these people are actually people that were around about the start of our country. And so this is the problem that they faced in the beginning of the country. And these are the different people that tried to work on the problem and came up with solutions. So the first one's Hamilton, and I believe talking about Alexander Hamilton, one of our founding fathers of the country, right? And then Thomas Jefferson, also one of the founding fathers of the country, and John Adams, his method for dealing with how we were going to give out seats of the House of Representatives to different states, and Webster's, and then also Huntington Hill's method. So there's 5 different methods we're going to learn. So here's some of the terminology. An apportionment method is it's a step-by-step process that guarantees the division of the seats to the states using some formula that is based on the party's populations. And you might be thinking, oh, well, wouldn't you just take the proportion of that state's population and then just give that exactly to the state? We're going to see that. But the big issue here with this we're going to find is that a lot of times when we say, oh, well, 10% of the population is in Kansas, so let's give them 10% of the seats in the House of Representatives. What often happens is 10% of a number is often a decimal number, like it's like 35.7, and we can't have 0.7 people in Congress. You can't have half a person in Congress. So the issue here that we're going to see is really, what do we do when we don't get a whole number of seats that we need to apportion? How do we handle that? Are we going to use simple rounding? Will simple rounding work? And we're going to look at different WIP methods that do work and ones that don't work. Okay, so here is some of the definitions. There's three elements common to all apportionment problems. There's objects or seats that need to be divided up amongst the states or the parties. About the seats are the set of identical objects, indivisible objects. You can't cut them up. Can't give somebody half of a seat in Congress. That are being divided among the parties. Yeah, those are the things being divided up as the seats. And then the parties are the states. The parties, they are entitled to receive items, and it's going to be a proportional. Ideally, we're going to try to do it as proportional as possible to the population that they have. That's it. That's the next thing that they say here. The population is the number used as the basis of the apportionment of the objects or the seats. So we're going to be handing out the seats in Congress based on the proportion of that state's or party's population. All right. Here is some other definitions here in section 4.1, apportionment. What we're going to do this, we're going to be using a standard divisor. And what a standard divisor is it's when we take the total population and we divide by the number of seats that we are trying to hand out. So let me just show you some notation for some of these things. So with the seats, we usually use the capital letter M to represent seats. And then with the parties, we usually use the capital letter N. And the populations are, we're going to see them, they're in positive numbers. And so like the population of the first state, if it's Kansas, we give it little lowercase p sub 1. And then the population of the second state, let's say, it's California, population, little lowercase p 2, sub 2. Okay. And then lowercase, and then maybe another state, Oregon or something, that's a population, lowercase p 3. Right. And then all the way to the last state would have whatever their population is. It's lowercase p sub n, because there's n different states. And then if we were to add up all of those populations from all the states, that would be equal to the total population, which we call capital P. And I'm just going to emphasize this, these are lowercase p's, right? Because that is a difference. They do make, that helps you to recognize there's a lowercase p. And here, this is an uppercase to be the total population in all of the states, also called the total population. It's an uppercase P that they like to use, okay? So the standard divisor, what it does is to calculate it, you're going to take the total population, and they like to use this SD for the notation. And they take the total population as capital P and divide by the number of seats that they're trying to hand out, whatever. And if we're literally talking about populations, then one SD is going to be the amount of people if we're talking about seats of Congress, the amount of people per one seat. And I'm just going to point out here, this is the total population. And you know that this fraction bar means division. So it means we take the total population and divide by the number of seats to get this standard divisor. And if I wanted to write this out in words, the standard divisor is the ratio of the total population to seats. All right, and then you have this second, now we talk about the standard quota. The standard quota is how much you would give to each state ideally. If it was a perfect world and like we could give a partial seat to, if we could give 35 and a half seats to Kansas in Congress to Kansas, then that would be the standard quota, is the actual amount of seats that they should get, even if it's a decimal number, which we know we can't give them. And they call this a fair quota, which I said, normally we can't give them the fair quota because it's a decimal number and we can't give a partial seat in Congress because you can't cut a person in half and say you can have half a person. So the standard quota is the exact number, fractional number. It's almost always a fractional number, but sometimes it can be a whole number. And if it is, we have no problem. It's just give them exactly that number of seats, and this whole the processes we're going to have to go to are not necessary. So the standard quota is calculated like this. And they use Q, the little lowercase q, to be quota, is equal to, this is lowercase p. So it's the state populations itself divided by the standard divisor. Okay, and they like to use this notation Q sub 1, Q sub 2, Q sub 3, and so on until the last state, which is there's an n state, so there's Q sub n. They like to use lowercase q's to represent the different quota for the different states. So like I said, if we calculate the quota, so we took that state's population, we divided by the how many seats they should get per person, or how many or so not, I'm sorry, it would be how many people per one seat if we divide by that, I'm sorry. And then we would get, let's say that we did that for a particular state, Kansas, and they got 35.5. So we owe them 35.5 seats in Congress. And like I said, we cannot give them half of a seat. So the best case that we could do, since we have to give them a whole number of seats, is we could either round this number up, and that would be called the upper quota. So it's the quota rounded up, so it would be 36, right? If we round 35.5 up, that would be 36. Or so that we call that number the upper quota. So the quota rounded up. What's the standard quota rounded up? And the lower quota is the standard quota rounded down. So like I said, if the quota, the exact quota, standard quota for a state were 35.5, then if we round that up, it's 36. The upper quota would be 36, and the lower quota, if we round it down, would be 35. Right? And you got to think about this as whenever we have a number like 35 and a little, and we have a decimal number, it's not a perfect whole number. This is the whole number part, and we have a decimal part. Whenever we have a decimal part, in my mind, it's like saying, I have 35 and a little more, right? So 35, and then when I see this decimal part, I see and a little more. So how do I find the upper quota and lower quota? Well, you just take 35. Well, you well, you ignore the decimal completely, just ignore the decimal like it's not there. So you would just go like this, and then the answer would be 35. So that's the lower quota. Or you say, well, if I have a little bit more than 35, what's the next consecutive number? And that's always your upper quota. So you get the lower quota by just ignoring the decimal, like it's not there. You get the upper quota by adding 1 to the lower quota. Okay, so hopefully that that helps you. All right, so moving on. Okay, so here's our first example. A hospital has 5 major units: emergency care, which is abbreviated by ECU, intensive care ICU, maternity unit MU, pediatrics PU, and surgery it's SU. There are 250 nurses working in these 5 units. Okay. So there are 250 nurses working in these 5 units, and they are apportioned to the units based on the number of beds in each unit, shown in the table below. So there's 20 beds in the ECU, 66 beds in the ICU, and 35 beds in the MU, 31 beds in the PU, and 25 beds in the SU. And they want to give the nurses out according to the number of beds each unit. They're going to assign different nurses to different units based on the number of beds they have. So they ask, what is the total number of beds or total population? So we add up all these numbers. So it'll be 20 plus 66 plus 35 plus 31. And we can do this in our calculator plus 28, and we should get 180. So the total population is 180. And they use a notation here, big capital P. Find the standard divisor and round it to 2 decimal places. So the standard divisor, if we look back up in our notes, the standard divisor is the total population, which we just calculated, divided by the number of seats. That's the item that you're trying to divide up. You're trying to share amongst all the different units. What are we trying to share in this situation? We're trying to share the nurses. We're trying to figure out how to hand out the nurses, right? So it's going to be 180 divided by the 250 nurses. 180 beds. Oh, I almost forgot. I changed this problem and I made it 50 nurses instead of 250. So make that change on your notes if I have not already made that. I think I probably already going to hopefully make that change for you. But anyways, let's say there's 50 nurses, just to make this problem a little bit easier to understand. Then we would do 180 beds. And between those beds, we're trying to split up 50 nurses. So we divide by 50. And I get 3.6. And that's 3.6. And I can, because I put the beds and I like to put the actual name of what the number I plug in. So it's going to be 3.6 beds per 1 nurse. So what does this standard divisor really mean? It means we should hand out 1 nurse for every 3.61 beds that each unit has. And you can't even have 3.61 beds, but we'll just go ahead and divide that by that anyways. So they want us to calculate the standard quotas for each hospital unit and round to 3 decimal places. The standard quotas are, and so to calculate the standard quotas, just a reminder, it's each individual state's population. In this case, the population are beds, not people, but beds, and then divided by the standard divisor, which we just calculated. So we just go, these are each of the units, and we now have states in this situation, we have units. So it's the standard quota is just the number of beds divided by the standard. So because for every 3.6 in 20, we're going to give them a nurse. So that's why we're going to do, to see, we're trying to find out how many 3.6s are in 20, we do that division, right? And then 66 divided by 3.6 and 35 divided by 3.66 or 3.6, sorry. 31 divided by 3.6. So all we're doing is take all the numbers, just divide by 3.6, right? By a standard divisor. Then this is the standard quota. So when I did 20 divided by 3.6, I got 5.555. So I can put that down there for ECU. And then I did 66 divided by 3.6, and I got 18.33. And they wanted us to do 3 decimal places. Oh, actually 555 should be 0.6. The last decimal there should be 0.6. Okay, and then the next one was 9.722. And then this one was, I'm doing 31 divided by 33.6. And I got 8.611. And then the last one, 28 divided by 3.6 is 7.778. And you can copy these answers down here. And just so that let's review one of the definitions for above, upper quota and lower quota. So I'm going to write the lower quota LQ and the upper quota UQ. So if I take 5.56 and I just ignore the decimal, right? Like it's not there, I would just have the number 5. So 5 is the lower quota. And then if I take the lower quota and add 1, that's 6. So the lower quota is 5 and my upper quota is 6. Because 5.556 is a number that's slightly bigger than 5 and a little more. Okay, then we have 18.33, which means 18 and a little more. So the lower quota is if I ignore the decimals completely, so ignore the 0.3333, I would just have 18. And to get the upper quota, I just take 18 plus 1, and that's 19. So the upper quota for the ICU would be 1819. Then 9.7, if I ignore the decimal, it's 9. And if I add 1, it's 10. So that's the upper quota and lower quota. And then for the pediatrics, if I ignore the decimal, it's 8. And if I add 1, it's 9. And then if I ignore the decimal for SU, it's 7. And if I add 1, it's 8. So basically, if we're really trying to hand out these nurses, and I can't hand out a partial nurse, like this says, okay, the EECU, you owe them 5.5555 nurses. You're like, what? I can't do that. I can't give somebody 5.556 nurses. So what's going to happen is the two closest things that I could do for them is I could round down and give them 5, that's the lower quota, 5 nurses, or I could round up and give them 6 nurses, right? And the same thing with the ICU. We owe them the fair amount of nurses is 18.333. We cannot give them 0.333. So we're either going to give them the lower quota, which is 18 ideally, or the upper quota, which would be 19, which would be generous, right? So that's what's going on with this lower quota and upper quota. Now, let's just see if we could just round general, just use the general rounding rule. And how many nurses would we be giving to everybody? So if we just followed the general, that's if 0.5, if somebody has 0.5 or greater, then you round up. If it's lower than 0.5, you round down, right? So it's 5.556. So that's going to round up to 6. So using the general rounding rule, I would have given this person 6 nurses. If 18.33, okay, well, that I would round it down. So I'd have given them 18 nurses. 9.7, I would have rounded up. So I'd have given them 10 nurses. And then with the pediatrics, 8.6, I would have rounded up to 9 nurses. And then 7.77, I would have rounded that up to 8 nurses. Now, if I add up all of those, okay, we decided we're giving the EECU 6 of those nurses. We're giving ICU 18 of those nurses. We were giving MU 10 of the nurses, and so on. So I add up all those numbers, 6 plus 18 plus 10 plus 9 plus 8, and I actually get 51. But I only have 50 nurses. We do not have money to hire, another nurse. There's just not money in the budget for that. So this is not an apportionment. That's not an apportionment because, and just taking regular rounding rules and applying them will not hand out the number of nurses we need to hand out. And it just doesn't work. We need to hand out exactly 50 nurses. And if we just use general rounding rules, it gives us the wrong amount of nurses. So this is not, and using the general rounding rule to just hand out what we should hand out is not an apportionment method. We're going to see other methods that do work, that always make sure to hand out the exact amount of nurses. And basically, we're just going to see different ways of rounding those numbers and making sure that we give out exactly the right amount of nurses. So that's an apportionment problem. But I just wanted to show you that just doing regular rounding won't work. So what does the standard quota represent? So it represents the exact amount of nurses that they deserve. What is the lower quota for each school? I wrote it up there already. It's under LQ. And then what is the upper quota? I already wrote that. And what do the upper quota and lower quotas represent? So in my opinion, it's the upper quota is the most amount of nurses that you would want to hand out. Like you owe the correct number of nurses. The fair number of nurses is 5.556. Okay, and so the two whole numbers that are closest to 5.556 are your lower and upper quotas. So there would be the second most fair thing to do, I think, like you'd either give them 5 nurses or 6 nurses. So the lower and upper quota are the most fair thing to do. And I mean, the most fair thing, I guess, is using the general rounding rule. You know, if you're under 5, then you go round down to 5 nurses, you know. But like we saw that it didn't work. But the second best thing is either give them their lower quota or upper quota. At least one of those are close to the amount of how much they should get. So I would say the upper and lower quota represent the closest whole numbers to the standard quota. And they would be the fairest. You know, one of those, either the upper quota or the lower quota, it would be the fairest. I would say giving one of those would be the fairest thing to do. So anyways, here's the second example, 4.1 apportionment. There are 430 seats in a particular county's Congress. According to a census, 10%, 10.85% of the country's population live in state A. Compute state A's standard quota. So we saw up here how to calculate standard quota. And we saw one equation. It was the population divided by the standard divisor. However, they don't give us the population or standard divisor in this situation. They just give us the proportion of the population for that particular state. And they also give us M, the number of seats. But an alternative way to finding the standard quota is just taking the percent of the percent of the total population for that state and multiplying it by the number of seats. That's another way of calculating it. So, and that's probably so I would turn this into a decimal. So I make it 0.1085 and then multiply it by 430. And I get 46.655. So that's just another way. And maybe you're like, how come both of those ways work? There's just more than one way to do things sometimes. So in this case, the standard quota for this state would be to receive 46.655 seats in Congress, which of course we couldn't give them, but that's a standard quota. So just showing you this example too is just showing you an alternative way of calculating the standard quota. If you're given the percent of the total population that a certain state has, then you can just multiply that times the it'll turn to decimal first and then multiply that by times the seats. So that's a second way of doing it. All right. Next, we'll be moving on to the first acceptable method. We saw a method that didn't work, just regular rounding. And 4.2, we'll see an apportionment method where we hand out all the right amount of seats or a fair amount of seats to everybody. And we also don't go over or under in the number of seats that we're supposed to hand out. All right. I hope you enjoyed this lecture. Have a good day. Bye.